So the next topic I want to talk about is tuning viscosity. You can imagine if you're a chef or a cook and you're making a sauce, the sauce might taste right, but it could be too watery or too thick. So what can you do about that? How can you tune the viscosity of your sauce so the consistency is just what you want, not just the taste profile? Um, oops. Just as a kind of quick overview, you just watched a video where they measured the viscosity of some different liquids. Uh, Typically, the way that you would do this in a scientific laboratory setting is using two methods. The first method is basically filling up a cup with a small hole on the bottom and seeing how long it takes for the liquid to empty out the hole. These are called Zahn cups. And that's a measurement of the viscosity. The faster the cup empties, the lower the viscosity. The slower the cup empties, the higher the viscosity. So you can actually even time it, and then there's a lookup table where you can determine, given the time, what the viscosity of the fluid is. The other approach is this falling sphere viscosimeter, where you drop a sphere into the liquid, and you're trying to figure out the viscosity of this liquid, and you see how long it takes to go between the start line and the end line. The lower the viscosity, the faster it'll take. The higher the viscosity, the slower it'll take. So by measuring the time it takes to go between these two lines, you can figure out what the viscosity of the fluid is. Let's say that in your kitchen you set up an experiment where you're trying to compare this sphere falling through a liquid. Let's just use marbles in this case. So we have 4 marbles, and then we have these 4 different liquids. One has water, one has olive oil, one has corn syrup, and then finally we have honey. So we can drop the 4 marbles simultaneously into the jars and then see how long the marbles take to reach the bottom. The faster, the less time it takes to reach the bottom, the lower the viscosity. Okay, so let's give this a try. I'll hit play. All right, very quickly, you could see that the marble hit the bottom in the water and the olive oil. So those must have fairly low viscosities. And one way you can think about what's happening here is that the water and the olive oil can quickly move out of the way to let the marble fall to the bottom. If we compare that to the corn syrup, which now is just reaching the bottom, syrup molecules, which are longer and are kind of more tangled together, it takes longer for them to get out of the way and therefore the marble to fall. And then honey is the longest, right? So those molecules really resist flow. And so it takes a while for the honey to move out of the way and finally reach the bottom. All right, here's just a concept question. I know there's an equation on this slide. Fear not, there's no math to be done, so don't be thrown off by that. But let's just read the question and see if you can answer it. A sphere is dropped into a viscometer filled with a mysterious liquid. If the sphere takes longer to fall in this liquid as compared to water, this suggests A, the mysterious liquid has a higher viscosity, B, the mysterious liquid has a lower viscosity, or C, the mysterious liquid has the same viscosity as water. So I'll give you 10 seconds to just ponder that and come up with an answer. All right, and so if it takes longer for the sphere to fall, that means that it's difficult for the fluid to move out of the way. It is resisting the flow, and the more the liquid resists the flow, the higher the viscosity. The answer here would be A. Okay, so we've talked a lot about viscosity, what it is, how to measure it, but how do you tune it, right? I keep on mentioning this idea that chefs would want to tune the viscosity of a fluid, and how would a chef go about doing that? Well, this diagram provides some insights. So here we have 1, 2, 3, 4, 5, 6 different substances. We go from water, which has a low viscosity, to chocolate, which has a high viscosity. And actually, if you just were to pour the liquid off a spoon, how long the stream is before it breaks into a droplet tells you something about the viscosity. So chocolate will go very far down before it breaks into a droplet, whereas water will quickly break into droplets as you pour it. And what we see here is that one way that we could change the viscosity, according to this little diagram here, is by adding some energy, by heating it up, right? So by heating it up, we're breaking some of the bonds between the molecules in the liquid, and by breaking those bonds, we're allowing the liquid to rearrange more easily, so it can get out of the way when you apply some heat. Another way that you can sometimes lower the viscosity of a liquid is by stirring it, by mixing it up. Again, you're breaking some of the bonds that are forming by stirring, and that reduces the viscosity. But neither one of these are particularly helpful when you're trying to create a sauce, right? Because the sauce, the temperature of the sauce is going to be determined by the plating temperature. You know, you're not choosing the temperature to get the viscosity, right? You're choosing it so you don't burn the mouth of the person who's going to eat the food, and you're not going to be stirring the sauces or trying to eat it either. So these don't really work as possible solutions. So the way that we typically think about tuning the viscosity of sauces is by actually adding particles, large particles, to the liquid. All right, so the picture down here, imagine this is your sauce. The blue background is the sauce. And I want to try to thicken up the sauce. One thing I could do is add particles to the sauce that take up space and get in the way of the liquid, resisting the flow of the liquid, right? So by impeding the flow of this blue liquid with all these red particles, I can increase the viscosity. All right, so let's imagine that you sprinkle some of these particles in your sauce. We'll talk about what those particles are later. And you've increased the viscosity some. What if you wanted to increase it even more? What could you do? Well, obviously you could just increase the number of particles that you sprinkle in. So here is the original picture. So I can double the number of particles. The other thing you can actually do is also increase the size of the particles that are already there. So if I can somehow get them to swell and become bigger, that's also going to increase the viscosity, right? So if I have a sauce and I want to try to make it thicker, so I want to try to increase the viscosity, I could either have the particles that are floating around in my sauce grow in size, or I can just increase the number of particles that are floating around in the sauce. Either way, that'll end up with a thicker sauce. So this idea of thickening a sauce by adding particles leads us to our equation of the week. So drum roll. Here we go. There it is. Now this equation looks this equation of the week looks quite intimidating, but fear not, it's not too bad. This part of the equation of the week is just telling us that the viscosity of a complex fluid, and a sauce is a complex fluid. So a viscosity of a complex fluid depends upon the viscosity of the simple fluid plus this function of this funny symbol phi. But don't worry about this expression, because really what I want you to understand this week is this phi, which represents the volume fraction. And the volume fraction, and you're going to be calculating this, is the volume of the particles dispersed in a fluid divided by the total volume of the fluid itself. Okay, so let's go ahead and get some practice with that, because I know that's a little bit difficult to just take in seeing the expression. All right, so here is our sauce. Our sauce is made up of this blue liquid background and the red particles in the sauce. The denominator here is going to be the total volume. It's the red plus the blue. So everything, I measure the volume of this whole big box, and I put that in the denominator. the numerator is just the volume of the red particles. So I have to figure out the volume of each of the red particles. I have to add those all up for the total volume of all the red particles, and that goes into the numerator. We call that volume dispersed because it's dispersed in this blue. These red particles are dispersed in this blue fluid. Okay, so again, the denominator is the total volume, whereas the numerator is just the volume dispersed. All right, so let's see what this volume fraction comes out to for some different examples, just to get a feel for what it is. Well, what if I were to just dump a bunch of marbles into a jar? What would be the volume fraction of these marbles in the jar? Now, the marbles are kind of just randomly positioning themselves, right? So I'm not neatly orienting them, I'm just dumping them in there. And it turns out if you do this, that the volume fraction is around 0.64. How do I interpret that? Well, the volume fraction is the volume of the dispersed, so that's the volume of marbles, divided by the total volume. That's the volume of the air plus the marbles, or just the volume inside the jar. So 0.64 means that 64% of the jar is filled up with the volume dispersed, which is the marbles. So the way I can think about what this number is telling me is it's telling me the fraction that's filled with whatever with the dispersed substance, in this case, the marbles. So 0.64 means 64% of the jar is filled with marbles, and the rest must be air. All right, let's try another one. This was a famous experiment that caught the headlines and got published actually in a pretty prestigious journal, the journal Science, where they looked at the volume fraction of M&Ms, which aren't spheres, so they're not like our marbles, right? They have a different shape. And what they found is that for M&Ms that you can fit in a certain volume, 68% of that volume is the M&Ms compared to our 64. Okay, so just throwing spheres into a jar, 64% is filled with the spheres. But throwing these, what are called spheroids, these M&Ms into a jar, I find that 68% of them fill up the jar. That's that 0.68 or 68.5. All right, what do you think is the largest number that this can be? It's the largest that I can fill this jar. What's the largest volume fraction I can have? Well, you can imagine, what if I somehow figured out a way to completely fill the jar with marbles, right? And by that, I mean there's no air. So somebody have to like deform the marbles and melt them or do something so that they're packed in with no air left. Well, then the volume in the jar will be all marbles, which is also the total volume. So you get these two numbers are the same. And if you do the division, it comes out to 1. So the highest volume fraction I can get is 1, which you're typically not going to get. But what we're seeing is values for volume fractions around 0.64, or in the case of M&Ms, 0.68. All right, what if I neatly arrange my spheres? Remember, in our marble example, we just dump them in the jar. What if I kind of position them in a nice lattice, like these oranges are positioned? And I were to keep on doing this and kind of fill the jar up, but neatly placing the marbles. What I'd find is that the jar is about 74% filled. Okay, and again, the goal here isn't to overwhelm you with numbers, but perhaps I've done that. It's just to get a feel for what this volume fraction means. And it's just telling you the fraction of the volume filled up by the dispersed substance. In this case, it was marbles, M&Ms, and now these spheres, which are neatly arranged. All right, so let's go ahead and try a practice problem. And I really want you to try to solve this one along with me. The struggle is where the learning happens. So just watching me do it is not going to be helpful on the exam. You want to get in there and make the mistakes, and it will serve you much better in the long run. So here's the question. There are 10 cups of water in a container. So I have a container, it can hold 10 cups of water. Okay, so there are 10 cups of water in a container that can only hold 10 cups. Otherwise, it begins spilling out. particles are added such that the volume fraction of the particles is 0.1. How much water spills out of the container due to the added particles? So these particles could be anything. I mean, let's just think about marbles, for example. So I have a pitcher of water, and it can hold 10 cups, this pitcher, and it's filled up to the brim with water. Now I begin dropping marbles in the pitcher of water. So because of that, it's going to add some volume, and the water is going to now flow over the edge of the pitcher. The question this is asking is how much water flows over the edge, how much spills out. If the volume fraction, the final volume fraction of the marbles added to my pitcher is 0.1. All right, so I'll give you a little bit of time. Let's take 20 seconds and really try to think through this and see if you can come up with an answer, or at least an approach. All right. So first, let's think about what this 0.1 represents, right? This 0.1 is the volume fraction. It's telling us the fraction of the volume filled with our dispersed substance, or our particles, or our marbles, if you use that example. So 10% of the jar, right, because 0.1 is 10%, is now filled with marbles. Oops. And if 10% is filled with marbles, then that must mean that 10% of the jar, which was water, got pushed out, right? Because that's now being replaced by these particles that we're adding. Well, what is 10% of the total volume? What is 10% of 10 cups? Well, 10% of 10 cups, that's 1/10 is 10%. 1/10 of 10 is 1, so it's 1 cup of water. So if I add marbles to my container such that the final volume fraction is 0.1, I would find that 1 cup of water has spilled out of that container, has kind of flowed over the side. All right, let's try another one. In mayonnaise, the volume fraction of oil is 0.8. So in mayonnaise, just a little bit of background, mayonnaise is a oil in water emulsion, which means you have all these little oil droplets mixed up in or embedded in the water. And according to this question, the volume fraction of all those little oil droplets in our water is 0.8. How many cups of oil are needed to make 3 cups of mayonnaise? All right. Again, I'll give you a moment to think about that. I'll check back in about 20 seconds. All right. So I'm going to try out this whiteboard feature here. So according to the problem, well, that one's pretty big. It's like a highlighter or something. Phi is, I'm going to make this smaller. I can't take it. Is 0.0, yikes, 8. All right, let me make this a little smaller. And that's equal to, much better. The volume dispersed, so I'll just call that VD, divided by the total volume. But we know that the total volume we're making is 3 cups of mayonnaise, right? So this is 3 cups. Just do a C. All right, so all you want to do is take this equation and solve for VD. And if you do that, what you'll find is that it's 0.8 times 3 cups. Which then comes out to 2, yikes, sorry, 0.4 cups. So that is the amount of oil you'll need, is 2.4 cups. All right, so, my guess is that some of you, this will come pretty easily. Others, you're going to struggle. I'm on Zoom, so please stop by if you have questions. Try out the problems in the packet. And again, if you're struggling with this material, stop by the Zoom session during class time, and I'll be happy to help you try to figure this out. All right, that's it for today. And I'm planning on posting Thursday lecture by Wednesday morning. All right, take care.